In this video, we will discuss the problem matrix exponentiation. The problem says that we have been given an equation of the form fn is equal to fn minus 1 plus fn minus 2, which is basically the Fibonacci series, and the first term, that is f of 0 is equal to 1 and f of 1 is equal to 1. So basically this is a Fibonacci series that has been given to us, and what we need to do is, our task is to find the nth number of this series. So in this case, if we have been given a Fibonacci series and like f of 0 has been given as 1 and f of 1 has been given as 1, so what we can easily observe is that we can simply apply the concept of Fibonacci series such that the ith term is equal to the sum of the I minus 1th plus the I minus 2th term. So we can say that we can simply run a loop. Let's say if we have to go till n, so we can say that we can simply run a loop from I starts from 2, I is lesser equal to n, and then I plus plus, and we can simply calculate the Fibonacci. That will be f of I is equal to nothing but f of I minus 1 plus f of I minus 2. But in this case, if we do it this way, so it takes order of n time, and that is a lot. So how can we do it much more optimally? So for doing this, we can use the concept of matrix exponentiation. The concept of matrix exponentiation will help us to calculate this in much efficient time. So first of all, what we can say is, like, I'll like to introduce you to a property, and before that I'll give a brief overview. So f of n is nothing but f of n minus 1 plus f of n minus 2, and f of n minus 1 is nothing but f of n minus 2 plus f of n minus 3. So you can say that similarly f of 2 is nothing but f of 1 plus f of 0, and we can notice that any term of this Fibonacci series can be represented in this format, f of 0 and f of 1. So any term can be represented by using these two terms. Okay, that is the main point here, that any term of this Fibonacci series can be represented by these two terms, because we can obviously observe that f of 2 is nothing but f of 1 and f of 0. So similarly it can be written in form of f of 3 and for larger numbers as well. Now what we need to notice is that if there is a property of Fibonacci series, and the property is that if we want to find let's say f of n and this thing, if we want to find the nth term like this, so this is equal to nothing but this matrix to the power n minus 1 into f of 1 and f of 0, this matrix. So basically this is a property of Fibonacci series which satisfies these conditions. So we can observe that basically what we have to do is, we have to take out, like, initially we can say that suppose this matrix is A, or this is the base matrix if we can say it, or the matrix A suppose. So we can say that this matrix is nothing but 1, 1, 0 and 1, and raised to the, like, we have to, like, if this is A matrix, so you have to find A to the power n minus 1 and then multiply it with this matrix, then we will get the final result. But in that case you will say that this is also taking order of n time, because if we are multiplying this n minus 1 times, so that again takes order of n time. But for this, what we can use is, we can use the concept of binary exponentiation. So for binary exponentiation, like, basically we can observe this part, that there is some multiplication that we are doing. A is like, we have to multiply a into a n minus 1 number of times. So in this part, what we can observe is, we can use the concept of exponentiation. And how? So we can say that we know that suppose there is a number like 2. So if I have to, like, suppose there is a number, let's say 3. So if I have to calculate 3 to the power 5, so either I can calculate it like 3 into 3 into 3 into 3 into 3, but that takes a lot of time. Again, order of n time it will take. But what we can do is, we can represent 3 to the power 5 as nothing but 3 to the power 2 into 3 to the power 2 into 3. Similarly, we can represent 3 to the power 2 as nothing but 3 to the power 1 into 3 to the power 1. Okay, now you will not observe that what we are doing, but basically the concept is that we'll calculate this once and multiply it. That is the concept. So let us try and see in terms of a bigger number. So let us say that we have to calculate a number, like let's say we have to calculate something like 2 to the power 16. So in that case, what we can understand is 2 to the power 16 will be nothing but 2 to the power 8 into 2 to the power 8. Okay, then 2 to the power 8 will be nothing but 2 to the power 4 into 2 to the power 4. 2 to the power 4 is nothing but 2 to the power 2 into 2 to the power 2. Then 2 to the power 2 is nothing but 2 to the power 1 into 2 to the power 1. Now what we will do is, we can see that basically what will happen is, we'll calculate this one time and then multiply. We'll calculate this one time, then multiply. We'll calculate 2 to the power 2 one time and then multiply it to itself. So that is how we are reducing the number of calculations. Because you can observe in this part that if we calculate 2 to the power 2 just one time, so we can get it. If we want to calculate 2 to the power 16, so if we have already 2 to the power 8 calculated, then we can multiply 2 to the power 8 and we can reduce a lot of calculations. And this is nothing but binary exponentiation. So for doing this, if you will observe, so what is happening? 2 to the power 16 is I've got it from 2 to the power 8, and 2 to the power 8 I've got from 2 to the power 4, 2 to the power 4 I've got from 2 to the power 2, 2 to the power 2 I've got from 2 to the power 1. So basically you can see that it is dividing by 2, right? So basically this is nothing but logarithmic of n. So I am able to calculate it in log n. Let us see what will happen in case of when the power is odd. So let's say if I had to calculate 3 to the power 9, or let's say if I had to calculate something like 3 to the power let's say 9 only. So in that case what will happen? It will be nothing but 3 to the power 4 into 3 to the power 4 into 3. So it will get multiplied, right? If the power is odd, then it will get multiplied once again. Okay, that is going to happen. And like 3 to the power 4 will be nothing but, again the same concept will apply. 3 to the power 2 into 3 to the power 2. 3 to the power 2 will be nothing but 3 into 3. Okay. So basically what we can understand is, we have to apply the same concept in the matrix part as well. Suppose in this case we have to calculate a to the power n minus 1, but suppose I mark it as a to the power x. So you can say that if a is the matrix, so you will calculate a to the power x by 2 into a to the power x by 2. Okay. Similarly, we'll have to calculate a to the power x by 2, the matrix. Then we will do a to the power x by 4 into a to the power x by 4. So that is what we will be doing for calculating this efficiently. And once we have calculated it, so what will happen? We'll be able to get the nth term, because we know from the property that f of n minus 1 is nothing but, it is equal to this basic matrix or the base matrix to the power n minus 1 and multiplied with f of 1 and f of 0. So after we have calculated the exponentiation for, after we have calculated for this matrix, let's say a to the power n minus 1, we'll simply multiply it with this to get the nth Fibonacci number, to get the f of n. Now this will take an order of log n time, because we are applying this property and then we are not taking order of n time, because what we are doing is, we are simply applying the binary exponentiation concept in this matrix. So this becomes matrix exponentiation. Now let us have a look at the code for better understanding of this problem. So what we will be doing is, we can say, what we'll be doing is, first of all we'll say that if n is equal to 0, then we'll return 1, because if n is that is given as the base condition. If n is equal to 1, then we'll return 1, that is also given. After this we'll declare a base matrix. Okay, we'll declare a matrix. First of all we'll have the base matrix and we'll declare it like this, like as I mentioned, 1 1 1 and 0. You can observe in this part, you can observe that is what we said, this matrix. Okay, then what we'll do is, we will have the initial matrix as well. So initial matrix will be nothing but f of it will indicate f of 1 and f of 0. Then what will happen is, we will calculate the power that we have to multiply it with. Okay, so we will calculate this, we will calculate a to the power n minus 1, this particular matrix that is there. So we'll calculate a to the power n minus 1, that is base matrix to the power n minus 1. So we'll calculate it, and we'll calculate it with the help of exponentiation, binary exponentiation. So if the power is 1, then we simply return the matrix. If it otherwise we divide it into half, like half is equal to n by 2. Then what we do is, we determine the matrix. So we will every time we'll be multiplying the matrix. Okay, so we will first of all calculate the answer, and then what we'll do is, after we have calculated, like let's say if the matrix was a to the power x, so I'll calculate a to the power x by 2, and once I've calculated a to the power x by 2 matrix, then I'll simply multiply it once again. So a to the power x by 2 into a to the power x by 2 will give me a to the power x. And if it happens that the number is odd, like if it is even, then I'll simply return. Otherwise, if it is odd, then I need to multiply it one more time. So I'll multiply it in and then return the answer. And like, what am I doing with this function? How am I going to multiply the matrix? So for multiplying the matrix, I'll simply, multiplying a matrix takes order of n cube time. But in this case, if we will observe here, so the size of the matrix is not too much, I think. So it will, like, size of the matrix is just 2 cross 2, so it will not take much time. So what we'll do is, we'll simply we'll apply the concept of matrix multiplication here, and then we'll return the overall multiplied matrix. So that is what we will be doing here. And after we have done this, so in the result, like, result will be what? Result will be nothing but whatever a to the power n minus 1 matrix we have got, that will multiply with the initial matrix that we had, that is f of 1 and f of 0. And after that, we'll simply return this value, that is this value that represents f of n. Okay, that is what we'll do. So this is how we do this particular question. And for solving this problem, it will take order of log n time, and the space complexity will be order of k, because like basically they will be constant space complexity, because we'll be also using some matrices. Thank you for watching this video. In case if you understood this explanation, so make sure to hit the like button and comment down understood as well. Thank you.